accelerator. Jefferson Lab has an educational mission as well. The Jefferson Lab Science Series features scientists and engineers who are gifted in making their work not only informative but fun. The Science Series is held once a month in the Jefferson Lab Auditorium. The presentation is live, spontaneous, and unrehearsed.
Good evening, everyone. It's on. Good evening. Good evening. My name is Nathan Isker. I'm the Chief Scientist here at Jefferson Lab, and I want to welcome you to tonight's Science Series lecture. It's a great pleasure for me to introduce tonight's speaker, who's a very good friend and a wonderful scientist. Howard Georgi was born in California, but then for some reason he bucked the trend and left the West Coast, went to the East Coast, where he got his bachelor's degree at Harvard, PhD at Yale. He went back to Harvard forever, moving through the ranks from a research fellow to a fellow of the Harvard Society of Junior Fellows, an associate professor, became chairman of the department for several years. He now has a chaired professorship at Harvard in high energy physics, theoretical high energy physics. He's the winner of many awards. He's been elected to the most eminent scientific bodies in the country, including he's a fellow of the National Academy of Science. He won the Sakurai Prize from the American Physical Society for his fundamental work in physics. He has also been very active in social issues in physics, including especially the role of women in physics. A typical afternoon in Howard's office, you will find him simultaneously editing the most eminent journal in the country called Physics Letters, working on a problem in theoretical physics, chairing the department, and babysitting, all at the same time. It's while he's asking you a question about your latest paper that you've been working on for a year and you thought you understood completely, he asks you a question that you realize you should have known the answer to. So all this happens simultaneously. It's very frustrating. I will not try to describe Howard's work in physics to you, but there has been a unifying theme to his work, which is the role of symmetry in physics. And that is also the theme of tonight's talk. The title is Symmetry, From Kaleidoscopes to Theories of Everything and Nothing. A great pleasure to introduce Professor Howard Georgi from Harvard.
Thanks very much, Nathan. It's wonderful to be here. And I'm experimenting on all of you because I'm not used to giving talks to people your age. So please, if I say something that sounds really stupid or that you don't understand, ask me right away what I'm talking about. Don't wait till the end. It'll go much more smoothly. Can we get rid of that light? Okay, thank you. So because it's important to be able to see the computer screen for what I'm doing. You've seen that one. I'm a particle physicist, and physicists in general try to understand the world and make sense of it all. But that's difficult because the world's a very complicated place. You know, there are complicated things like you, which are made of smaller things like cells, which are made of smaller things like molecules, which are made of smaller things like atoms, and so on. atoms are made of electrons and nuclei, and as far as we know, electrons aren't made out of anything. So they are fundamental particles, the kind of thing that particle physicists like to study. But the other component of atoms are nuclei, the kind of things that are studied at this laboratory, and the nuclei are made out of protons and neutrons, and the protons and neutrons are made out of quarks. All those things are studied at CBAF. Again, the quarks, as far as we know today, aren't made out of anything, so they may be fundamental. But this process of seeking simplicity is basically what we do. And we work very hard at it. A typical experiment in particle physics involves some huge machine that's designed to isolate the properties of these tiny fundamental particles. Now you'd think that after all that effort that things would really be simple. And we've gone some way towards discovering really simple, beautiful rules. We've got some glimpses of things that are really gorgeous. But there's a lot of stuff that looks complicated still. It doesn't quite make sense. So our suspicion is that we're not yet at the heart of many of the issues that we want to study. And in some cases, we know that, and that's really what I want to talk to you about today. But you might ask, what does simple mean? And often, at least as far as I'm concerned, simplicity has a lot to do with symmetry. When something is simple or beautiful, it's often because there's some symmetry built into it, like the symmetry of the kaleidoscope that I used for the title of the talk that you see up here. What is symmetry anyway? Well, it's one way of thinking about it is that a symmetry of something is a transformation that you can make that gives you back the same thing. Like in the case of this kaleidoscope image up there, if you take it and rotate it around the center of the image by 360 degrees divided by 7, that is a seventh of the way all around the circle, you get back to the same thing. So this has what you might call a sevenfold symmetry, symmetry under rotations by 360 degrees divided by 7, whatever that is. You are probably all better at division than I am because my brain cells are tired. That's an example of something called a discrete symmetry, because you can't rotate by any old angle. You have to rotate that kaleidoscope image by exactly 360 degrees divided by 7 to get back to where you started. But you can imagine that there are continuous symmetries as well. In fact, if I were to build a kaleidoscope with a continuous rotation symmetry, it might look something like this. The trouble with this thing, it's easy to build that kaleidoscope that you saw on the first screen with a couple of mirrors and some pieces of glass. I don't exactly know how to build this object except electronically. On the other hand, it's a great screensaver, I think, for hypnotizing people. So you're all going to major in physics. Well, perhaps not. But at any rate, this object has a continuous symmetry. I can rotate this by any angle, and it looks the same about the center. Now, both continuous and discrete symmetries are very important in physics. In this talk, I'm going to, because they're generally more important for particle physics, I'm going to concentrate on continuous symmetries like those small rotations that are possible for that kaleidoscope. Questions up there? Again, please ask questions right away if you have questions. Okay. One of my favorite kinds of symmetries are symmetries under translations. For example, something that is kind of important is the symmetry of translations in time, without which it would be rather silly to do physics at all, because if you can't, if things don't look the same today as they looked yesterday, that is, if the laws of physics change with time, it's going to be very difficult to figure out what's going on. But fortunately, that seems to be a pretty good symmetry of what we know in physics. And it's responsible for all kinds of regularities that we see in the world. For example, the fact that clocks tick at regular intervals. Here's a nice system, which unfortunately doesn't show up very well on the computer screen, but you can sort of see it, of a mass bouncing back and forth on a spring, ticking out regular time intervals. And the fact that that period doesn't change as you move along in time is a consequence of the fact that the laws of physics are not changing with time, this symmetry under translations. In fact, this one's kind of neat. That curve underneath is a very special thing. It's a cosine curve, which I'm not going to subject you to much mathematics today, but it's worth saying that that curve is special because it's actually related to something that's very simple, just uniform circular motion. If I have something going around in a circle at a constant speed, its two coordinates, its x-coordinate and its y-coordinate in time, trace out those, that nice harmonic curve, which is very important in physics for that reason. Okay. Now, another important symmetry is the symmetry of translations in space. And there again, there's a simple physical system that illustrates that nicely. If I have a rope and I stretch it, it has a possible motion which consists of a traveling wave that just moves along forever without changing shape. Now, why do I care about that? Well, waves, it turns out, are kind of important in physics. It's because physicists have difficulty telling the difference between waves and particles. And it's not really our fault. It's because of quantum mechanics that is somehow built into the way the world works, that tells us that particles and waves are really just different aspects of the same thing. Now, in a way, that's not so surprising, because if I have a particle, what is it that's special about particles? Well, for example, particles carry energy and momentum. So now I need a volunteer in the audience. Catch. Okay, good. You felt when you caught that, the energy and the momentum associated with the motion of a particle. Now, here I have a rope. Can you help me a little further? Great, thank you. If I can get, whoops. This is a dangerous demonstration. If I can get my rope untangled here, we'll see how it is that a wave can carry energy and momentum as well. It's actually kind of hard if you have a wave that's a boring thing like that thing that we saw on the computer screen, which just goes on forever and ever. On the other hand, if I put a lot of these waves together, I can make something which is called a wave packet, which actually kind of moves along like a little particle. And, well, I've run out of space, so I guess that's far enough. There we go. So if I send a little wave packet at you like this, you can see that it moves along somewhat like a particle. And in fact, you can catch it if you lift up your end of the rope just as it reaches me. Try to send one at me. I can catch that wave packet. There we go. That's better. Okay, thank you. That packet, thanks very much, is a combination actually of lots of these infinitely long waves in such a way that the energy and momentum is concentrated in a little region of space and moves along at a constant velocity because of the translation invariance of space. So you can maybe begin to believe that waves and particles might be different aspects of the same thing. But obviously that's not all there is to it. There's a lot of weirdness to quantum particles. For example, a wave can have any amplitude you like. I could have made that little packet that I sent at you less steep and have it sort of disappear. But a particle is either there or it's not. So particles, unlike a classical wave, particles are quantized. Also, waves can bend around corners, and classical particles can't. If I throw my tennis ball at you, it goes in a straight line unless it bounces off something. It never bends around a corner. But in fact, because of quantum mechanics, waves and particles share all the same properties. Waves get quantized, particles can bend around corners, and strange as all of that is, it's all true, and it's just the way the world works. Now, you might ask, if particles are waves, what is it that's waving? It's a fair question. Sometimes we actually know the answer to that. For example, in a light wave, we know that what's waving is lines of electric fields, the sort of things that are produced at positive charges and end at negative charges, like the field lines that you see around a magnet. If you, let's see, what number am I at? Okay, 6. If I sprinkle iron filings around over a magnet, you get these pretty little magnetic field lines. In the same way, there are electric field lines that begin at positive charges and end at negative charges. Now, if I let me stop that. If I have a single positive charge with no negative charges around anywhere, it just radiates these lines of electric field off in all directions. Now, suppose I take a positive charge, which is radiating these lines of electric field around in all directions, and all of a sudden I start it moving. Well, what happens then is illustrated in this picture, I hope. No, wrong one. This picture. There are the lines, oops, there it started moving. And what you see is that there's a kink in the lines associated with the acceleration of the charge. Those kinks that radiate out from the position of the charge is actually the light that's produced when you accelerate that charged particle. Electromagnetic waves then are associated with the waving of these electric field lines. And all of that is very well understood, but even though it's been known for years and years that these are waves, we now know that they're also particles. Light consists of photons, particles of light, and if you turn down the intensity of one of these waves, you can see it break up into individual photons that hit you one at a time. But sometimes we don't know what's waving. And it's that situation that I want to talk to you about today. Because there's a more mysterious wave that is something of great interest in particle physics today, which is a kind of ripple in the vacuum. It's a wave in nothing, sort of. I don't know how to describe it, because I don't really know what it is. But curiously, even though I don't know what it is, I can tell you a lot about its properties because of symmetry. And that's what I want to try to explain today. I'll also try to explain why it's important. Are you having a little difficulty following me? Questions about what's happened so far? Okay, whatever. Before I talk about those, I want to talk a little bit more about weird quantum things. Quantum weirdness. My very favorite quantum weirdness is something called spin. Well, you know, it's obvious what spin is. You spin around. And probably lose your microphones in the process. But the spin is a property of many particles, which basically is classically very much like spin in the sense that these particles carry something called angular momentum, which is a quantity that particles carry when they're spinning around some axis. It's points in a direction. It's what we call a vector with a direction and a magnitude for a classical particle. Now, spin is weird. Like particles, spin is quantized. There's the smallest possible unit of this angular momentum, which is called h bar divided by 2. That little h with a line through it is called h bar. Stands for Planck's constant divided by 2 pi. And that divided by 2 is the smallest possible angular momentum that anything can have. Now, this is a very small angular momentum, which is why you don't know about it in everyday life. If I have a bacteria or something that twists around every few years, it has about that amount of angular momentum. So that's not very much spin. Anything bigger than a bacteria which is spinning at all just has an angular momentum which is enormous compared to this smallest unit of angular momentum. So you don't care that there's a smallest unit in everyday life. When a skater is turning around, it's not at all interesting to the skater that there's the smallest possible unit of angular momentum because the angular momentum is so big. But it is very relevant for elementary particles because they're the smallest things we've got around. Now, the weird thing about a particle with this minimum possible angular momentum is that it's so weird I don't even quite know how to say it. It's what we physicists say is that it has 2 spin states. What that means is something like this. If you have a classical spinning particle, it's spinning around some axis with some magnitude. So you can measure the x and the y and the z components of its angular momentum, and then you can figure out what direction it's spinning in. For a quantum particle, it doesn't work that way. For a spin-a-half particle, which is what we call these things with the minimum possible angular momentum, because we get tired of saying h bar all the time. So we use units in which h bar is equal to 1. Not sure what sort of a quantum glitch that was. For a quantum particle, if you measure the spin around any axis, you always get plus h bar over 2 or minus h bar over 2. And when you do that, you destroy all information about the components of the spin in the other directions. So in a certain sense, you then know what direction it's spinning in also, but it's because you happen to measure the spin along that particular axis. And if you then go and measure the spin along another axis, even though you know it's spinning that way, you'll discover, sure enough, the spin is plus a half or minus a half along that axis too. It's crazy. It doesn't make any sense. That's the way the world works. And this is all tied up with rotations, because if you measure the spin along one axis and get plus a half, say, and then you take that thing and rotate the whole system down to another axis and measure the spin along that axis, you'll get plus a half again. On the other hand, if you rotate it down and then measure it around the initial axis, you'll get plus a half the time and minus a half the time, completely at random. So what happens is that rotations mix up those 2 spin states in some well-defined way, but it's pretty mysterious. Now, the crucial thing here is that what makes all this interesting is that the order of rotations matters. And that's something which is easy to see. Whoops, that's still going. Let's do a little experiment here. Suppose for this experiment, I'm going to get down on my knees a little bit. And now I'm going to turn 90 degrees clockwise around a vertical axis. So an axis up like that. If I'm looking down on me and I turn 90 degrees, that means that was counterclockwise, right? Imagine looking down on me. Here I go. Now I'm turning clockwise. Now I'm going to turn 90 degrees clockwise around an axis out towards you. So looking at me, you should see me moving in the direction of a clock face. So let's see, that means that I go like this, right? Whoop. Oops. Well, I wasn't face down, I'm face up, but it's all right. Anyway, I'm over that way. So remember my position here? Good. Now let's do it the other way around. Let me now first turn 90 degrees along the axis out towards you. That's like this. And now I'll turn clockwise 90 degrees along an axis, the vertical axis, which means like so. And I end up in a rather different position, right? So the point is that the order of those rotations makes a difference. I don't know if I got them right there, because it's hard to think about what direction you're turning when you're lying on the floor, but the important thing is that the order matters. And what's neat, the reason I like this so much, is that the intertwining of the spins that comes from rotations in different directions allows you to understand completely how the two spin components get mixed up, basically without doing any work. All that matters is that you understand how what happens when you first do one rotation and then you do another. And that subject is the mathematics that goes with that is something called group theory, which is neat because it's really getting something for nothing. It tells you that you can understand what happens to the two components of that little spinning system just purely from the mathematics without knowing any physics at all. And getting something for nothing is fun, so I've always liked this subject. In fact, when I was younger than you, I read a quotation from Arthur Eddington, who was a famous relativist, a famous theoretical physicist of a previous generation, who said something like this, describing what was fun about group theory. We need a super mathematics in which the operations are as unknown as the quantities they operate on, and a super mathematician who does not know what he is doing when he performs these operations. Such a super mathematics is the theory of groups. What he's describing is this process of getting something for nothing by knowing the structure of the rotations without actually knowing what it is that's being rotated. So anyway, little did I know when I read that when I was 14 or something that I would then spend the rest of my life applying group theory to various different situations. Okay. Now, why is this interesting to particle physicists? Well, it turns out that all of our theories of the forces that cause particles to clump together and transform into one another and do interesting things are built on this same mathematics. In particular, what I'll talk about today is something called the weak interactions, which causes some radioactive decays and also, well, it's something we can study in various ways at particle accelerators. And it's based on a weird analogy with this lowest possible quantum spin, in which two different particles play the role of spin plus a half and spin minus a half. In particular, the neutrino and the electron behave like a pair of things connected by rotations. And similarly, the up quark and the down quark behave like a pair of things connected by rotations. Now this is an analogy. These are rotations not in ordinary space, like with me rolling around on the floor there. But so you have to imagine that there are rotations going on in some completely abstract quantum mechanical space. But because group theory doesn't care, because this super mathematician doesn't care what quantities he's operating on, the mathematics is exactly the same as for the rotations of one spin state into one another. And the weak interactions are described by a theory that has a rotation symmetry in this fictitious space, except for one thing, which is that the symmetry is broken. This would be just like the symmetry of rotations if the electron and the neutrino were completely equivalent, the way upspin and downspin are completely equivalent because you can get from one to the other just by turning yourself upside down, and obviously that doesn't matter to the laws of physics. This matters because the electron and the neutrino are very different particles. The electron has charge, it has mass. The neutrino doesn't seem to have any of these things. Nevertheless, this symmetry is built in to the structure of the theory. So what's happening there is that somehow the state of the world, the vacuum state, the state with nothing in it at all, is breaking that symmetry between these two spin states. And that's what I mean by a theory of nothing. I should say that these symmetries of, like the rotations of the two-dimensional, of these little pairs, may be extendable into something like a theory of everything. It's possible to put together this symmetry of the weak interactions and the symmetry of the strong interactions that's studied at the Jefferson lab into a larger symmetry in which you really describe all of the forces that we see. But that whole thing is based on somehow being able to break the big symmetry down to allow you to distinguish electrons from neutrinos from the other particles. So how does that work? Well, I want to spend the rest of my time trying to give you an idea of what goes on there. And you're really going to have to bear with me because I'm going to try to build a model. That's what I do to try to understand physics. I build models. It's like playing with Legos. You build a model to try to capture the essential physics of what's going on. And in this case, I'm going to try to build a model to capture the essential physics of this breaking of the rotation symmetry. And so this is going to be a model of nothing. It's going to be a model of the state of the world in which there are no particles. Let's see. Where am I? Okay. So this, unfortunately, is rather dim. I couldn't get it any brighter with this equipment. But what you see there, can we just have the lights down for a second? What you see on the screen is a two-dimensional lattice. Can you see that? Okay. You see it actually in perspective, so it's sort of coming out at you. And this is a weird model. My model of space, the points in space are going to be the places where those lines intersect. So that's a little weird. Space is a lattice. It's not continuous the way we know it really is. But those are the breaks. Oh, thank you. Now, of course, I can't see to do anything, but it doesn't matter. We'll push buttons at random and see what happens. Now, at each point on this lattice, each point of which describes space, there's going to be a little corner which lives in a different space. This little corner, in fact, lives in the fictitious space that I was talking about, associated with rotating the two spin states of the neutrino and the electron into one another. And the thing about a corner, if the screen were a little brighter, what I would do is to have the 3 axes here in different colors. I couldn't do that, it just didn't show up at all. But this corner is supposed to be labeled with 3 different colors, so you can tell which is the x direction, which is the y direction, and which is the z direction. And then that little corner specifies a particular direction, a particular coordinate system in this fictitious 3-dimensional space. So that's the idea. Now, the way I'm going to build this model is that I'm going to put one of these at every point in space. Whoops. There we go. And they're all going to be free to rotate around in any particular direction. So there they are rotating around one axis. There they are rotating around another axis. 1, 2, 3, 4. Here I hope they are rotating around the 3rd axis. Any of those things are allowed. Okay? And in fact, I'll try to build, I'll imagine that I can build my model so that all those directions are completely equivalent. If they're all completely equivalent, I might as well just pick one of them and say, well, that's going to be the orientation of this corner in the state in which there's nothing going on. That's as good as anything else. Now, the other piece of physics that you need to build this little model is something that allows neighboring corners to sense what their neighbors are doing. For example, you could put little magnets on the ends or something so that neighboring corners want to align with one another. In that case, the lowest energy state of this system is going to be one in which all the little corners are aligned, like that. They're all lined up in the same way. It doesn't much matter how they're all lined up. They might all be like that, or they might all be like this, but they're all going to be aligned in the same way. And again, since that's the situation, we'll just say by that is the situation. Okay, so now what happens next? Now, that describes the model, but the point is that, well, first of all, I should warn you that this is not a great model. Nevertheless, it does really stupid things, like, for example, I treat the points in space as discrete, just these points on the lattice. And that breaks the rotation symmetry of real space that I know actually exists. That's good, okay. So that's not very good. But the good part about it is that it gets the symmetry of the little 2-dimensional pairs in the weak interactions exactly right. It picks out a coordinate system in the space in which these guys rotate and breaks the symmetry and then allows me to distinguish between the electron and the neutrino. Now, I haven't put anything into this model except nothing as yet. That is, all this model does is to give you a model of the state in which there are no particles. I haven't put in the electron or the neutrino. I haven't put in the quarks or anything else. Nevertheless, there's something interesting in this model. And what's interesting is that the individual little corners that are free to rotate in various directions can wave. In particular, if I have an infinite number of friends and they hold down all but one of these little corners, and I twist one of them into another orientation and let it go, it'll oscillate back and forth. It's a typical situation where if it's out of alignment with its friends, it will realize that and it'll start to accelerate up towards the position where it's aligned, but by the time it gets there, it'll be moving. So it'll have some inertia and it'll keep going, it'll overshoot. And that's the classic recipe for oscillation. So it'll just oscillate back and forth. On the other hand, if I now don't have an infinite number of friends, which is actually the case, if I just take one of the corners, which I can do all by myself, and suddenly move it out of alignment, what happens is a little more interesting. And here it is. what happens is that I get a ripple effect in this collection of corners. Because when I move one in the middle, the ones right outside it realize that they're not quite in alignment with it, and so they start to move. Then the ones beyond there start to move, and so on. And so you get a rippling of the misalignment of the corners out from the central point where you first moved something, just like ripples in a pond spreading out from a place where you threw a rock in. So that's what's going on there. Now those ripples are waves. And waves, according to quantum mechanics, are the same thing in a sense as particles. So this model of the nothing necessarily has in it some particles that are associated with these ripples in the vacuum. Ripples in nothing. Okay. Okay, so those are ripples in nothing. Now, the point is that what this model is supposed to show you is that those ripples always exist. Anytime you build something that breaks the symmetry in the state of nothingness. Because to do that, you're going to have something that's free to move around in all directions and is coupled together with its friends so that it picks out a state in which they're all aligned in the same way. And as soon as that happens, it can always wave. And in fact, the properties, though I'm not going to explain this in detail, the properties of those waves, like the properties of the spin states themselves, are completely determined just by the fact that rotations in different directions, the order matters. Again, it's all fixed by the group theory, almost all. But that's all I can say about it at the moment. Now, in fact, the connection of all of this with particle physics is that there are some heavy particles which are produced at a few particle laboratories around the world called the W+, W-, and Z, which are responsible for the weak interactions in the same way that photons, the particles of light, are responsible for the forces between charges. And part of these particles are those ripples of the vacuum. Those ripples in the vacuum are incorporated into these three particles. And in fact, the three different planes of rotation, possible planes of rotation in this fictitious space, correspond to these three particles, the W+, W-, and Z.
So would you say that the area that you call nothing actually had those particles in it, and that's what caused the wave?
Am I saying that the area that has nothing in it actually has particles in it? No, not quite, but close. What is true is that the ripples get incorporated into these particles. The state in which nothing is happening really is the vacuum state. There's nothing there. But because of the way the state is built, those ripples are possible, and therefore these particles are possible, and so you can make them at accelerator labs. Okay? Does that help a little? Other questions? I can't see you, but shout out questions if you have them. Okay. Now, there's just one more thing I want to say here. I want to show you how ripples scatter off one another. Now, you might think that these ripples wouldn't really scatter off one another at all, because, after all, the ripples are pretty much nothing. In fact, if you make a very big ripple, it looks exactly like nothing, because if it's big enough, all of the corners inside it are pretty much aligned and moving very slowly, and so they look just like the vacuum state. Might be the wrong state, they might be pointed in the wrong direction, but all those directions are equivalent, so every vacuum is as good as every other one. So you might think that if two of those things passed through one another, nothing would happen. And that's not quite the case for a reason which is very easy to understand. In fact, you already understand it. So let me show you how that goes. I'm going to actually do this with the scattering of wave packets, like the wave packet that I sent to my assistant in the audience on the rope. I'm going to construct a wave packet which is very long. So what's going to happen is that we'll be going along and there'll be nothing there, and all of a sudden some of the corners are going to move out of into a different orientation. And then they're going to stay in that newer orientation for a while, and then they're going to rotate back. And that will propagate through space. And that process looks like this, I hope. What happened? There we go. Okay, so we're going to see a wave packet coming in from that side in a minute. Yeah, here it goes. Now, and they're rotating down, and then after a while, the back half of the wave packet will come through and rotate back. Pretty boring, huh? Okay, now, thank you. Now let me scatter two of these things. I'm going to have one wave packet come in from this side, and then while it's there, another wave packet will come in from the other side. So here comes one, twisting the particles down, like this. And here comes another, twisting them in the same direction this time, but from the other order. You see what's happening? A sort of plane of, or line of corners is moving all at the same time. Now here comes the second half of this wave packet, and it's twisting these things halfway back. And then the second half of the other wave packet comes through and twists these things the rest of the way back. And as we sort of expected, we're back, when the second wave packet is finished passing through, back to vacuum, back to the state of nothing, so no particles are left in the end. But that's because I had both wave packets twist the corners in the same, along the same axis. Suppose instead I have the first wave packet twist the particles along one axis. Here it comes. Can people see this? I can't tell, so I know what it's supposed to look like. And now this one is now twisting. Here comes the second wave packet, twisting the things up along the other axis. And now the second half of the first wave packet will come through and untwist along the first axis. And then the second half of the second one will come through and untwist along the second axis. But now you will observe that the system is confused. And we've gotten back to a state which is a perfectly good vacuum state, all right, but it's the wrong one. The little corners are now pointed down. The reason is that the order of the rotations matters. So if you first twist along one axis and then along another, you have to go back in the opposite order and first untwist along this axis and then along the first axis. And that's not what these wave packets did. They twisted along one axis, then along another, then along the first one, and then back around the second one, and that, because the order of the rotations matters, you end up with a different state than you started with. Now, in fact, if it were just that, you just end up with a different vacuum, and that wouldn't matter very much because all the vacua are equivalent. But the only reason that anything happened was that the two wave packets overlapped in space. That first one thing came through, then the second one, and the second half of the first one came through before the second half of the second one was had arrived. So it's only when the wave packets overlap that you get this effect. So if you look down on this model, this Lego model of nothing, from the top, what you'd see is something like this. You'd see the two wave packets coming down from the two sides, but then where they overlap, you'd end up with the wrong kind of vacuum, and it would realize that it's the wrong kind of vacuum at its edges and start to radiate ripples in all directions. And so what would happen in this process is that the two wave packets would give you non-trivial scattering. They'd produce more of these funny vacuum ripples. And that's a typical thing that particle physicists study, the scattering of two particles to produce lots of other particles. Okay, that's really what I wanted to say today. The point is that scattering is a very simple and inevitable consequence of this simple fact that rotations don't commute. But we particle physicists think it's kind of important because we don't understand what these ripples are really made of. And our standard mechanism for understanding what things are made of is to scatter them on one another and see what happens. Now this is a case where we can do this scattering and know that the scattering is going to take place in a certain way just from the symmetry. But it turns out that as we go to higher and higher energies, eventually that simple picture that I've given you, which is just based on the symmetry structure of the model of nothing, has to break down. I don't have time to explain why that is, but it has to do with quantum mechanics and the fact that eventually this scattering becomes so strong that the whole picture breaks down. And at that point, something interesting has to happen, and our hope is that if we manage to do scattering of these vacuum ripples from one another, we will be able to see that interesting physics and figure out what it is that's actually waving to produce these ripples in nothing that gives rise to this part of the W and the Z particle. And in fact, that turns out to be, in my view, one of the most interesting questions in particle physics, because we can't understand how to go beyond these our present fragmentary theories to real theories of everything until we understand this physics of nothing. So let me stop there and ask for questions. Yeah?
Just so I understand what you were doing earlier, you have let's say you have a vacuum with nothing.
Yep.
Run some waves through it, change the state of it, and you end up with another vacuum of nothing in a different state.
That's right. Now, but what happens is the following. That state only appears in the little region where the two wave packets overlapped. The question was, just to repeat what happened when the scattering takes place and you end up, after the scattering, with a vacuum that's oriented wrong. If that were the case everywhere in space, it wouldn't matter so much. But the point is that it only is the situation in the small region of space where the two wave packets collided, where first one half came in, then the second one, then the end of the first one, then the end of the second one. If the first one gets all the way through some region of space before the second one gets there, then they untwist back to the original vacuum. And that's the situation almost everywhere. But in this little path where the two wave packets overlap, you get the wrong vacuum. Now the wrong vacuum looks around and it says, gee, there's all this right vacuum nearby. I must be in the wrong orientation, and it starts to untwist. And it's that untwisting that gives rise to the scattering. Okay. But the important issue, the important thing is that the existence of these nothing waves in the first place, it's that's so mysterious and that we need in order to understand how these theories can have symmetry and yet the symmetry not be realized and yet the electron and the neutrino can be different. Other questions? Yes, back there.
Maybe I missed it. What's the significance of the math?
Ah, yes, I didn't say the significance of the map. The map is a planned accelerator at which this scattering is going to take place sometime in the first decade of the next millennium. This is called the LHC, the Large Hadron Collider, built at a lab, the lab CERN, which is centered in Geneva, Switzerland. And it's, I don't know, I guess you can't see the scale here, but it's several miles around. It's similar to the relation between the electric force and photons, but is fundamentally different, and it has very different properties. It's conceivable that